So first of all, thank you for the invitation and good morning. Today I will be presenting you my thesis work that I presented last year in November. So this was part of my 4-year thesis. And what I did in this thesis was trying to integrate deep learning processes in embedded platforms, specifically in a GPU FPGA embedded platform. And this work was supervised by François Berry in the Institut Pascal, Maxime Pelka, that you already know pretty well. So basically, what we have been doing these years is trying to incorporate some deep learning processes into embedded platforms. Our team has a good expertise in smart cameras, and a smart camera is actually just a containerized processing device close to a sensor. In this case, an image sensor. Normally, these smart cameras are completely containerized in a way that they do the processing inside of the device, and then they communicate this processed or these obtained features to a centralized network or through a communication network. Here you can see a quick example of some of the work that we have done in our team. This is a 3D visual odometry using a specific smart camera. This smart camera, as many of our solutions, includes an embedded FPGA. And as you may already know, in the last decade, the FPGAs have been a popular solution to deploy artificial intelligence and machine learning algorithms on the edge, compared to more traditional or more de facto solutions like CPU, GPUs, or ASICs. And as you can see here, this is some forecast that Acronics, one of the manufacturers of the PGA in the industry, have been envisioned during the years. And as you can see, the growth of this kind of solutions is becoming more and more popular. So there is gaining some momentum. This momentum seems not to stop quite soon. So the GPU in green, it's the CPU, GPU, and ASICs in green are still growing, but not as fast as the FPGA and embedded FPGA solutions. Also, from the perspective of research, we have seen that FPGA have also been a popular deep learning accelerators since an early stage. So first, the first stages of deep learning were mostly in a theoretical approach, like Rosenblatt's perceptron. Also, where was backpropagation. And after a couple of decades afterwards, we saw the birth of FPGAs in 1985. Soon after, we started to see the first CNN layer, convolutional neural network. And 1 year after, we saw the first GPUs from NVIDIA. And soon after, once we established like a well-known theoretical background for CNNs, and we had also a good base for hardware, some research were quite attracted by this ecosystem, and we started to see the first papers using FPGAs as deep learning accelerators. So in the early stages, there weren't that many. Well, like a couple of them in the IEEE Explorer, and everything exploded once, as you may already know, as soon as some big CNN networks were starting to arise, like AlexNet. And soon after, and then the following years, we started to see more and more papers using FPGAs as deep learning accelerators. And this tendency started also to grow, not only in the industry, but also for research. And each year we see this number of papers doubling. And as soon as last year, when I presented my thesis, this tendency was still growing. So last year we had over 500 papers, so it's still doubling each year. I don't know if this year we're going to start seeing some slowdown, or if this tendency is going to keep up. But at least there is still some stages to mature these technologies. In our team, the Dream Team, as part of the Institut Pascal and the ISPR, we have many solutions with embedded smart cameras from different approaches, like low resolution, like panoramic views, stereo vision. And in my thesis, I will be working with, I was working with heterogeneous smart cameras. In this case, the one I will be covering is our prototype called Chimera. Chimera is a embedded smart camera that includes multiple processing cores, multiple processing devices, specifically CPUs, FPGAs, and GPUs. This smart camera was the result of a high processing demand that we already saw in the industry and also in research. So it was the result of these requirements from the industry and research to deploy deep learning algorithms. Of course, these processing demands have some requirements like a high component integration, a high complexity, and of course, it is not easy to develop for all these processing devices in this environment. So we have to develop some expertise on different programming and also hardware frameworks. The good thing is that we're not alone. We're still in the age of CNN accelerators. FPGAs and GPUs are not the only solutions that we can find as CNN deep learning accelerators. And for example, we have Google's Coral TPU, the tensor processing unit. We have Intel's neural compute stick. This is actually the second version of their solution. And we have also big players like NVIDIA's Jetson family. All of these three solutions are embedded solutions, and each one of them has a different accelerator paradigm. Like for example, incorporating CPUs and GPUs or ASICs. Yeah, just to say that we were not the first ones working with heterogeneous embedded accelerators. However, in my thesis, what we are trying to include is this hardware awareness to the development stages. For this, we are like establishing some important research questions, like how can I efficiently deploy my CNN topology on my embedded heterogeneous smart camera? How can I bring this to my hardware? How can I split my CNN? And of course, how I'm going to map each single partition that I already decided to my heterogeneous smart camera. In this case, what I'm going to present today is how we did this CNN splitting, partitioning, and mapping into our prototype, the Chimera camera. For this, we focus on three main contributions. The first one is the modeling. This is the characterization of the smart camera. The second one is the partitioning, how I'm going to split my CNN model. And the third one is the optimization. This is how I'm going to map efficiently these partitionings, or how to do it in an automatic way to ensure a good performance on my platform. The first contribution, the modeling, what we're trying to do is to characterize how our smart camera is going to be evaluated. And for this, we need to establish or to decide which measurement we're going to use to know how good it performs. And this is what we're going to call the key performance indicators. These are some measurable values that we can obtain from the performance of my camera. For example, the time it takes to finish one task, how much energy it takes to finish this computation or communication. But also we want to know which features we can use to characterize my smart camera. The second contribution is the partitioning. This is how I, from a complex CNN model, how can I break it down to smaller pieces? These pieces is what we are going to call the accelerated partitions. And there are many questions like, oh, okay, which granularity I should choose to split my CNN model, and how can I split it better to have a better performance on my CNN deployment. The third and last contribution of the thesis is, okay, now that I have break down my CNN model in smaller pieces, how can I try to formulate an optimization problem from these pieces, taking into consideration some of the constraints from embedded devices, like, for example, the number of logic and memory elements that I have in my device that I can use to map my CNN. And I always like to do this analogy of Lego blocks. First, we have our CNN model that we break down into like Lego block or Lego bricks. And for example, we want to build a big pyramid, but we have to take into consideration some constraints like the balance of this pyramid and the number of blocks that we can use without breaking this balance. So what we're trying to formulate an optimization problem with the selected KPI, the key performance indicators that we had, like the time, taking into consideration these constraints. So this is an optimization problem that takes into consideration the design space exploration. So for this presentation, these are going to be the three main aspects that I'm going to cover from the contributions. These are where the modeling, the partitioning, and the optimization. At the end, I will present a small demo with our prototype Chimera. And of course, I will finish with some conclusions. Okay, first, we are going to be covering the modeling, what we call flydeling. I will cover that in a minute. But first, we must know what mathematical modeling is. For that, just in a general manner, just imagine that we have a system. A system is just a physical representation of natural phenomenon. And we cannot change anything from this system. All we can do is try to put some inputs into the system, and we can observe how this system performs depending on these inputs. And the mathematical modeling is just a mathematical formula that tries to describe this system or this physical phenomenon, given the inputs and the outputs of that we observe. So this is just a general way of seeing the mathematical modeling. Really simple steps. Going a little bit further into robotics. So we have a system. Just imagine like a robot arm, and I can try to manipulate this robot arm, giving it some excitation sequence. This could be a lever that I move from left to right, trying to control the robot. And I can do it at several speeds. So I can go really slow, sorry, and see how the robot performs. Or I can be moving the lever from one side to the other really fast. And I can see how this robot is going to perform in both cases. So what I'm trying to do is trying to find a model that more or less resembles this system. And we're going to try to estimate a similar nature of the robotic arm. Depending on how good our estimate is going to be, we will get some error. And what we call here the response, the error, and the estimate are the observations. So this is what we can measure from our system, the estimations that we observe from our model, and of course the error that we is a comparison of these two observations. However, depending on this error, we can try to adapt our model, and we try to perform a little bit better, and hopefully this error is going to diminish over time. Unfortunately, it's, well, I don't know you, but I'm quite lazy. I don't want to be moving the lever at different speeds, like from really, really slow to really, really fast. There is an infinite number of speeds that I have to increase. And for that purpose, in order to have a big response of the system, of the robotic arm, we want to play with all the possible speeds. The good news is that I don't have to do it manually. There are some excitation sequences that exploit the whole spectrum of frequencies. And actually, this excitation sequence is quite simple. It's just a white noise or a Gaussian distribution. And one of the properties of this excitation sequence is that we have a infinite spectrum response. So just instead of trying to manually move the lever from one side to the other, we can just do it randomly in a Gaussian distribution. And we can ensure that our system, that the observations that we take are going to represent the whole spectrum of the system. Now, this is from a robotics perspective. How can we apply these concepts to our CNN and heterogeneous smart camera? Well, we have our system with different processing devices, the CPU, GPU, and FPGA. And we want to know how good is it going to perform given a CNN model. So we have an excitation, random excitation sequence of the CNN, and we're going to observe how good is it going to perform on each single device. So we have, again, the KPIs, the key performance indicators. Remember, these are just measurements. For example, the energy, the time it takes, and the resources. Unfortunately, for robotics, it works pretty well just using a random excitation sequence over time. But for CNNs, this is not possible because CNNs are time agnostic. This means that they are not time dependent. The CNNs take one image or one feature map and processes the whole event. There is no concept of time between these events. So we cannot use this excitation sequence as it is, or an excitation sequence that is time dependent. So we have to adapt a little bit these concepts to our CNN use case. And for that, we have to understand the main aspects of the CNNs. So probably you already know, but the most consuming or the most power hungry part of the CNNs are the CNN layers, of course. And it's better to spend more time trying to understand these CNN layers than some other computations, like the fully connected layers, or displaying layers, or doing some pre-processing on the CNN. So we are going to be focusing more on the CNN layers, since this takes most of our time. In order to excite our system using a stochastic sequence, first we need to know what we are going to use as a sequence. For this, we're going to use two different excitation levels. What we call first the structural level. The structural level is just the shape of the input tensor that we're going to use. in order to feed our system. And for that, we have the input feature map, which is just the size of the shape of the input tensor. This is the height, the width, and the number of channels that we're going to process in the case of a two-dimensional convolutional layer, but also the size of the kernel filters. So we have the size of the kernel window K, and the number of the kernel filters N. So this is the structural level, and this is what we require to perform some convolutional operation. This spits out some output feature map, but we're mostly interested in these features or these convolutional layer properties. The second level of excitation is the data level. And what we're trying to do here is trying to modify each single value of the input tensor. Instead of trying to play with the shape of the input feature map, we're trying to randomly change the values of the input feature map. So in this case, we can use the same concept of the Gaussian distribution to insert some noise into the system. And now we can use these two concepts, the structural level and the data level, to fit our system. So we're using a black box approach as the same principle as I presented in the robotics use case, but we're changing a little bit the way we're fitting this our system, our platform, our heterogeneous platform, and we're exciting in a structural and a data level way. Again, now we can start to get some observations from the system, and we're going to store these observations, these KPIs, in our dataset. So, for example, we input one layer with a specific structural shape with a given random values, and we get some performance indicator. For example, a given energy. Now we can start to think how we can create a model to get close to the system, to resemble a little bit of the system. And remember, from the modeling, what we want to do is to obtain this mathematical expression and try to get close to the system. So what's inside of this black box? First, we are going to use a technique called ensemble modeling. Ensemble modeling is just using small models. In this case, we're going to use flight weight models. That's where the name flightlink comes from. And these small models are going to be combined in a way that we can create a more complex model from these smaller or simple models. So what we're going to do is we're going to have a feature that we want to model. We are going to have some regressors, like a traditional regressions, like a linear regression or quadratic regression or non-linear regression. We have multiple regressors. And what we're going to do is we're going to make them compete. And the one that has the lowest error is the one we're going to choose as a winner. So this is a competitive ensemble modeling. However, this is only for one single feature. If we want to extend this to multiple features, first we have to replicate the same principle to multiple features. For example, in the structural level, the height of the input feature map, the width, the number of channels, and the properties of the kernel filters. And for each single one, we're going to repeat the same process. So we already excited our system. We know the inputs. Because we fed our system, we already also know the observations, the outputs of the KPIs, and we created our dataset. So now from this dataset, we can split it on each single on each single regressor or ensemble modeling, and we're going to choose from each single feature a winner. And from each single winner, we're going to combine them in order to get a multivariate model. And this multivariate model is what we're going to use to estimate the output of our system. So at the end, we're going to add to our dataset also the estimation that we got. And we use a traditional supervised machine learning method to validate the performance of our estimations. This is normally used. This is normally done using k-fold cross-validation. So here we have some results of the flydalling, of the flyweight modeling. In this case, I'm checking I taking track of the energy KPI. This is my observation. And we have three different devices. In orange or red, you have the CPU. In green, you have the GPU, and in blue, you have the FPGA. This is a color code that I'm going to use for the rest of the presentation. And we have different structural level configurations. For example, the number of filters in each convolutional layer, and also different kernel sizes. So here we keep fixed the size of the input feature map, and we're playing only with the kernel filters. Let's do a little zoom on one of these use cases. So the solid line is measured the actual real-time measurements of the CPU. I'm going to show at the demo, and the dashed line are our estimations. So most of the time it works quite well. There are some extrapolation error for flydalling, but most of the time it works quite well with an error of 7 to 10%. And of course, we did all this for each single device in our heterogeneous platform. So for the CPU, GPU, and FPGA. So now we have models that can estimate the performance of each single device given a configuration of the CNN layer and also the values of the CNN layer. This was our first contribution of the thesis. The second one was the partitioning techniques. I'm going to go quite fast in this part, since these were mostly adaptations of already existing techniques. So the second contribution was, okay, we have this CNN model, we have this algorithm that can be represented as a directed acyclic graph or a directed cyclic graph in the case of recurrent neural networks. And we want to split it in order to have a partition on the FPGA and a partition on the GPU. So we're trying to have these two partitions, and we want to have a subgraph to map on hardware. Of course, there are some questions like, okay, I can split it per layer, I can split it per channel. How can I divide the inputs? And what we decided at the end is, okay, we're going to do a mixture of everything and try to do a module level partitioning. And a module level partitioning is a combination of the partitioning per layer and also per channel and the size of the shape of the input feature map. So without getting too much into details, I'm going to cover four partitioning techniques. The first one is the depthwise separable convolution. The second one is the group convolution. Third one is fused layer, and the fourth one is tiling. These are techniques that have already been widely used in more recent CNNs. However, what we did during the thesis was to try to adapt this to heterogeneous platforms and try to, in a naive way, how to find a good partitioning into our heterogeneous platform. So first, covering the depthwise convolution. This is a traditional convolution, and it has some number of MAC operations. This is multiply and accumulate. The idea of the depthwise convolution is like factorization. We're going to try to reduce the number of MAC operations by dividing the traditional convolution into two parts. The first one is the separable convolution. This is just a 2D convolution done per channel. And afterwards, I'm going to do a pointwise convolution, which is just also a traditional convolution, but the kernel filter is just one by one by the number of by the length of channels that we have on the input feature map. So we're just like factorizing the traditional convolutional layer into two parts. This is a sequential execution, and the advantage is that we're reducing the number of MACs by a factor, given by the size of the kernel filter, and also the number of kernel filters. A heterogeneous way to do this is, okay, we have some part that we are going to put on the GPU. This is on green, and and the second part is the one we're going to put we're going to map on the FPGA. Why to map the pointwise convolution on the FPGA? It's mostly because on the FPGA we have less resources rather than on the GPU. On the GPU we can multiplex over time different channels. This is really good for processing over batches, where the GPUs are normally outperforms the FPGA, but the FPGA is quite good at trying to process when the weights of the kernels are closer to the logic devices, to the logic blocks. So in this case, because we're having kernel filters with one by one convolution, it's better to keep this on the FPGA in order to reduce the number of resources. The group convolution is a little bit simpler, because what we're doing is just taking the traditional convolution and we're splitting the in a channel-wise partitioning. So we're just going to choose the number of channels we're going to map on the FPGA and the number of channels we're going to map on the GPU. And at the end, we're just simply concatenating these results. This is what we're going to present at the end of the demo. The fused layer is similar in the way that it is a sequential execution of the CNN. But what we're trying to do is, okay, we're keeping multiple layers on a single device. For example, we can have 2 layers on a FPGA if we have enough resources, and multiple layers on the GPU. This takes more time because we have to multiplex it, but we can execute multiple layers on the GPU. The big advantage of fused layer is that we don't have to do inter-device communication. We don't have to take the output feature map and transfer it to another device, because the communication is done on the same device. This is normally way faster, so there is some speed up in terms of communication. And finally, the tiling is probably the simplest of the partitioning techniques, because here we're splitting the input feature maps while keeping constant the kernel filters. So by splitting the input feature map, it's just splitting in terms of the height or width, or also also the it's mostly the height and the width of the input feature map. This was the second contribution of the thesis. The third one was the optimization formulation of the partitioning automatic partitioning selection. And in this case, okay, we have already a CNN layer. We have some techniques that give us a way to split these partitions. Remember, to get these Lego blocks, these building blocks. And from the first contribution of the thesis, we have also a way to evaluate these partitions on the FPGA, on the GPU, or on the device that we already model. For that, we use a single objective problem formulation. Remember, it's just like trying to build a block pyramid given some constraints, for example, the balance or the number of blocks that we're using. In a more formal way, mathematical way, we have an objective function and some inequality and equality constraints. We have everything because from the Flydling, we obtain the models, the KPI Flydels as objective functions, and also we can use them as constraints. Depending on the mathematical properties of the objective function and also the constraints, we can use several approaches to solve this optimization formulation. If everything is linear, we can use linear programming. However, if we are having some, as you remember from the Flydling technique, there were some regressors that were non-linear. So if one of the winners of these regressors is no linear, then we cannot use linear programming, and we have to use more powerful techniques like geometric programming, generalized geometric programming, or more complex tools. I'm not going to get too much into the details, but these are just non-linear optimization tools. Of course, if we are achieved to formulate everything with linear programming, the solution is quite easy, but the formulation to get everything into linear is quite complicated, and sometimes it's actually impossible. So there is some trade-off into solution, and with solution I mean the time it takes to solve this problem, and also the formulation. Okay, so as you may remember, we have these properties from the CNN, the properties from the input feature map and from the kernel filter. And what we are trying to find is the properties that we want to map on the FPGA and the properties that we want to map on the GPU. Remember, blue FPGA, green GPU. We can simply try to minimize one of the KPIs, for example, the latency or the time it takes to do some computation. Well, to do some task. This is, for example, the computation. We can do it as in a sequential manner. This is the time it takes to do the computation of the FPGA, the time it takes to do the computation of the GPU, but also we have to add the time it takes to do the communication between these devices. So now, from simple models or Flydels that we obtained from the first contribution from the modeling, we can play around to create some objective functions to characterize our heterogeneous platform. Additionally, we can use the models that we obtained, for example, the resources, as constraints. For example, we have the number. Don't pay too much attention into what one of these is. This is just logic and memory resources that we have on our FPGA. The important part is that every time we try to map something into the FPGA, we're going to start to exhaust some of these resources. And we have to be careful because these resources are finite. So we cannot map everything on the FPGA. So these are our constraints. This is the number of building blocks that we can put inside of the device. And of course, we have some partitioning constraints. This is, okay, However, I split my my input feature map or my kernel filter. I have to respect that the combination of all these of the features on the FPGA and GPU are processing the whole layer. Unfortunately, depending on the formulation, sometimes it's not that easy to have a simple solution depending on our objective function. One of the contributions that we did in our thesis is, okay, we're going to, from a non-linear optimization tool like generalized geometric programming, we're going to make it simple in a geometric programming way. I'm not getting too much into the mathematical details, but what we're trying to do is to simplify or to make it easier for the optimization tools to solve this in a polynomial time. So for that, we have to relax some of the equalities into inequalities. This is some of the main, one of the most difficult constraints that we have in geometric programming. Is that we have to respect these inequality constraints. So we have to force some equalities into these constraints. And what we're doing is trying to algebraically manipulate these constraints to transform it into these inequality constraints. I'm not getting too much into the details, but if you're familiarized with optimization problems, what we're going to do is try to penalize this objective function. So we have here our classical traditional objective function, and we're adding a penalization term depending on this algebraic manipulation to simplify it to an easier solvable objective function. And depending on the solution that we obtain from the relaxed problem, we're going to increase the penalization. So if we're not getting a good solution, we're going to start to penalize more and more until we get an acceptable solution. As an example, we have here a CNN layer with 16 channels, and we're going to split it into the FPGA and the GPU. So first, we split it, and the algorithm gives us, the optimization geometric programming tool gives us a solution. Okay, it's telling us, okay, we have 16 channels. You want to reduce the latency, for example. Okay, so do one channel on the GPU and one channel on the FPGA. This is not an acceptable solution because we want to split the 16 channels. Remember, we have to follow the constraints, and the partition constraints are telling us to split the 16 channels, not only two. And because this is not an acceptable solution, we relax that much the problem that we're getting unfeasible solutions. We have to penalize against the objective function. So we increase the penalization term, the penalization weight, sorry. And for the second solution, we get a slightly better solution, but still it's not 16. We're not splitting the 16 channels. So we keep increasing until we get an acceptable solution. This acceptable solution is when we get the splitting of the 16 channels. For example, here we got a solution that's okay, split 14 channels on the FPGA and the 2 remaining channels on the GPU. So this is already an optimized solution for our platform, given the objective and constraint models that we obtain. And yeah, we obtain this in multiple solutions of polynomial time, which is also polynomial time. We can extend this solution not only for the FPGA and GPU, but also for the CPU in Orange. So now we have our whole heterogeneous platform characterized, and we have the partitions for a given layer. So this is for a given layer. To extend it for multiple layers, the only thing that we have to do is we have to manipulate a little bit our objective and constraint functions. And in a linear manner, we have only to sum each single of the single layers. This is a more interesting full CNN network. This is ResNet 18. Remember, we're focusing on the CNN layers. So we have 17 layers. And for each single layer, we have different partitionings that we split in our heterogeneous platform. These are simulation results. This means that we didn't test it on our prototype, but we're assuming that if we have multiple FPGAs or a big FPGA, we can get this kind of solutions. So for each single layer, we have different partitionings, and in red here we have the speed up on each single layer. As you can see, the biggest speed up is on shallower layers, where most of the channels are mapped on the FPGA, and the lower speed, the weakest speed up is on the deepest layers, on the deeper layers, which are mostly mapped on the GPU. This is mostly because on the FPGA we don't have enough resources to map everything. So we try to map most of the layers that are MAC intensive, and on the GPU, those are more memory intensive. Finally, I will show a small demo on Chimera. Chimera is the prototype we achieved during this thesis. Chimera comes from a coprocessor heterogeneity integration for smart cameras. And we included an embedded GPU from the NVIDIA Jetson family. This is the NVIDIA Jetson TX2. And an embedded Intel FPGA. And we did intercommunication between them with PCI. So we're just sending between them input feature maps, input and output feature maps. The main workflow of Chimera is, okay, we have a CNN, a pre-trained CNN, and we create a CNN model that we're going to split into our CPU and GPU, and some part of the model. This is Onyx for those that are more into developing with high-level frameworks like PyTorch. We create a small subgraph that is going to be split into the FPGA. We use some proprietary tools to compile and to synthesize to our devices, in this case for the GPU and for the FPGA. And we program our FPGA with this given programming files, and also for this compiled binaries to the GPU. So we're splitting the pre-trained networks to our hardware platform. From a development perspective, we have been developing this communication between GPU and FPGA in high programming tools like PyTorch. And for those that are quite familiar with PyTorch or high-level programming tools, we included a library to communicate the GPU with FPGAs on Chimera. And this is quite simple because we're just transferring input and output feature maps to do the processing and communication. As a quick example, really quick, is we're going to do a heterogeneous solver. So we're going to take an input feature map, an image. We're going to do a convolution or a 2D convolution, and for this input feature map, given a fixed kernel window for X and for Y. So we're going to try to find the borders or we're going to detect the edges of on the image. So we have these two kernels. that are going to work as kernel filters for our convolutional layer. We have the properties of an image, and we're going to split each one on the GPU. We're going to split one filter on the GPU and one filter on the FPGA. Just give me a second. Oops. Yeah, it's running. Okay, so here we have a. Can you see the image? I'm not sure if you can.
Absolutely.
Yeah, okay. So here we have an input image, and here at the right we have the measurements of the CPU in red again, the FPGA in blue, and the GPU in green. As you can see, the FPGA is constant because it's already programmed. This is one of the properties of the FPGA. We have to program it every single time we want to execute a given CNN layer, and these real-time measurements are the ones we use to create our data set. And for example, here we have the results of the GPU. Here I'm doing the processing of several frames. So these are the spikes that you're looking at right now. And yeah, this is how we created our data set. For example, here we're measuring the power KPI. This is the performance in power of Chimera. So finally, as a conclusion, I presented my work of the thesis that we finished last year. We had three main contributions. The first one was the hybrid accelerator characterization. We're using a system identification black box approach that we call flightling. It works most of the time. It has some issues with extrapolation, but yeah, around 7% error. I presented also some adaptation of heterogeneous partitioning on embedded platforms. And also, I presented the third and last contribution. I presented optimization problem formulation using what is called geometric programming. And we relaxed the more complex problem called generalized geometric programming into geometric programming. This allows us to solve the problem in polynomial time and to automatically get these accelerated partitions. This would be everything from my part. I would like to thank you for the attention.
Thank you very much. Question time.
I don't know if you have any questions. Aussi, si vous voulez les poser en français, moi, je peux arriver à me débrouiller.
Yes, on the optimization, you say you optimize computation and communication.
Yes.
You are two important parts. But in the modeling part, you've talked only about the modelization of the computation. How do you model communication?
Yes, that's an excellent question. Yes, in the actually we mentioned some of the KPIs. We didn't mention all of them. Actually, hold on a second. I think it's very easier to see here. Yeah, we mentioned some of the KPIs, but not all of them. And for example, here we also created some models of the resources that we took into the FPGA. And for the communication, we did exactly the same. For example, this is latency or the time of execution, and we did exactly the same. We took the structural level of the input feature map. We measure how much it took to do the transfer from the FPGA to the GPU and back. So we had this still the same principle of random excitation of the system, and we keep track of everything. We kept track of the observations we took from the communication time. So it is the same. The communication is treated as the same as a computation. Of course, our model doesn't know that it's communication, but yeah, we create a model to track this communication part.
Okay, so that means that you have multiple, because in your modeling you are talking about single layer. Sorry. So now you are also in your modeling part, you have multiple layers to communicate at some point.
Yes.
Okay.
Yes, indeed.
Okay, that makes sense. Thank you.
No, thanks.
I also have a question about the modeling part, actually. At some point, you said that you were mostly interested in layers in the modeling for signals without any time dependencies. So basically, you are focusing on convolutional neural network.
Mm-hmm.
Does it work with the networks, more recent network, where you actually have time dependencies between layers, like recurrent neural networks or transformers or stuff like this?
Yes, this was one of the many discussions we had. We were, yeah, of course, mostly focused on CNNs, but yeah, it would be interesting to try to incorporate some stochastic sequences that actually consider time dependency. It doesn't make that much sense on CNNs. Actually, those were our first results. What we were trying to do is like trying to completely transfer the principle of system identification from robotics to design space exploration, and we try to transfer most of the principles to the CNNs, and we observed that including some time dependencies actually didn't change anything on the CNNs, so there were no which confirmed our hypothesis that that the CNNs are time agnostic, and it doesn't change anything if we try to modify the input feature maps with some time-dependent sequences. Indeed, I think that that could be something that could be explored for example, like for recurrent neural networks or for LSTMs, where time dependency is actually an important factor. We haven't explored that well, this approach, but I think it's something interesting there. Yeah, of course, we have to reformulate how we excite the system in this case. I don't think that using non-time dependent sequences would be a good idea in this CNN model and this kind of deep learning models.
Okay, thank you.
Going back to the CNN, the input data that you send is a completely random image, but there could be even just 0 or whatever. It's random. There could be only 0 because, from what I understand, both your platform are time constant depending on the data. Your system is not time dependent, and I don't know about energy. Maybe it's linked to energy. I don't know.
I don't know if I understood well the question. Is the question if
is it really independent from the data? Because if you send a real data, compared to random noise, is your CNN going to execute in a different different execution property? Like do you see variation in time or variation in energy?
Yes. This is something that I didn't cover that much on. Well, I didn't cover at all in the presentation. But one of the observations we had during the dataset generation while exciting the system is that compilers, especially for the GPU, are really smart right nowadays. And also synthesis tools for the FPGAs are also really smart. So for example, if you're trying to send them really sparse feature maps, what you are mapping on the platform gets optimized. So if you are training your models, when I talk about models, it's regressor models. When you're trying to models with only sparse feature maps, then you are going to bias a little bit your models to perform well on cases where the feature maps are sparse. On the other hand, if you train your models with values that are, for example, only 1 or 255, then you are forcing your platform to do the whole computation. But this is not always the case, because as I said, compilers are really smart, and synthesis tools also for the FPGA are really smart. So for example, if you're giving values of multiple of 2, so for example, if you have like 2, 4, 16, 32, blah, blah, blah. Also, the FPGA is really smart in knowing, oh, okay, so your weights are, or your values are only, I can code your values and shifting only the 1 bit in our weights. So it's important to have like a big representation or an expressive enough random sequence for the values of the input feature map. Not only zeros or 1, but everything, because we don't know what will end up mapping on the embedded platform. This is the good part of the black box approach. In some cases, okay, you don't really care what you're how you're excited, what you're mapping into the system or how it does it. But what is important is that you try to exploit the whole configurations of your system. I don't know if my answer was a little bit
you went much further than what I expected, and
yes,
it was way more interesting than what I was asking. So yes, I thought about the data. I didn't thought about the weight, but you are able to optimize the
I mean, it affects both. It affects both. If when you excited the system, you have to excite both the weights, because we're also exciting when we talk about the CNN layer, we're exciting the feature map and also the kernel filter. So you have to excite both.
Yeah, but your compiler is not going to optimize based on the data value.
No.
May optimize based on to do your constant multiplication or whatever, if it finds votes, but based on that, okay.
Exactly.
Yes, it's very interesting. Thank you.